Hello, today we're going to talk about friction. And actually, before we get into that, we're going to talk about what forces look like on an incline. So, um, when we have forces on an incline, there's some important things to think about, but one big thing is that we are going to want to tilt our axes for our free body diagram. So normally we have it just, horizontal and vertical, but we're going to want to tip it so that the vertical component is perpendicular to the incline, and then the horizontal component is along the incline. So that's what's happening here. If you just look, we have the y-axis perpendicular to the incline and the x-axis along the incline. And what happens is a couple of things. This allows the normal force to just be in the positive y direction, because otherwise the normal force would be at an angle because it's perpendicular to the surface. And if the surface is an incline, it's at an angle. But it does make the weight force at an angle instead, because the weight force is always going to point straight down. So it doesn't matter that we tilt the axis, that's doing nothing to the weight force. The weight force is just going to stay directly straight down. But we tilt the axes because one of these forces has to be at an angle. And there's a lot of other things that make it a lot easier for the weight force to be the one that's at an angle instead of the normal force. And we will spend some time with this, but you'll notice that with the dealing with a vector at an angle, we break it into components. We've done that before, but the x and y components are not the same as when we were doing acceleration, like in projectile motion. So in projectile motion, the acceleration, or no, the velocity in y was usually sine theta and the velocity in x was cosine. But what we're going to find with putting or tilting our axes is that the y component is going to be cosine and the x component is going to be sine. And we'll, like I said, we'll look at this more, but it's because when you tilt the axis, the angle of the incline is also this angle between the weight force and the negative y-axis. But again, I'll show you more on that. But the big thing to be careful about when you're dealing with an incline is that your normal force needs to be perpendicular to the surface. So if it's on an incline, don't just put the normal force straight up. That's not perpendicular. Remember, normal means perpendicular. So make sure you don't do this one, you do this one. And then when we've tilted the axes, the weight force needs to point straight down, not along the negative y, straight down. So those are just things to look out for, and we'll do some problems with this, so you will see. Now, let's talk about friction. Friction is when two surfaces come in contact with each other, they have these kind of like small pieces of the surfaces, like really microscopic level, that catch on each other. And that causes friction. That just adds an additional force. And friction depends on what the two surfaces are made out of. We'll get to that. So we've already talked about how there's two types of friction. There's static and kinetic, and how static friction is when something isn't moving and kinetic is when it is moving. But now we can learn a bit more about the distinction between those. So this is just an example of a free body diagram of this person pushing a box or a crate or something. And so we have our pushing force, we have the static friction force, which is in the opposite direction of the intended motion, because this is static friction, so we're not moving. And we have our normal and weight force. So the thing about static friction is that it's only as big as it needs to be. So it is only trying to balance things so that no acceleration is happening. So, for example, if you push with a smaller force, the static friction only needs to counteract that smaller force. Because it doesn't want to then cause acceleration backward. That's kind of opposite of what it's trying to do, is trying to keep things where they are. So as long as it balances the force that wants to get things accelerating, the box won't move. So if we start with a smaller push and our friction force is small, but the same magnitude, then we increase the size of our push, the friction force gets bigger to compensate. And then finally, we reach a maximum value of the static friction force. And then after that point, the object will be able to move. Because the force you're applying overcomes the friction force. So the equation we have for static friction is this, we're used to the symbol for static friction. It's just like a curly F with an S, is less than or equal to the coefficient of static friction times the normal force. And I actually have those labeled here, so I'll just give you both of these. So this is just the general equation for the coefficient of, or for static friction. Because again, it doesn't need to be its maximum size, because it only needs to be as big as necessary to prevent the acceleration from happening. But the maximum is the coefficient of static friction times the normal force, excuse me. But again, important point with static friction is that it's only as big as it needs to be to prevent motion. So kinetic friction is easier because it doesn't have it's just a one value, one size fits all sort of thing. And so kinetic friction equation is just force of kinetic friction equals the coefficient of kinetic friction times the normal force. And so it isn't affected by anything like how fast an object's going, what forces you're applying to it. It is just the coefficient of friction, so the two materials that are sliding across each other, and the normal force, which the normal force can, change based on the situation. But beyond that, the kinetic friction is constant. And so you can think of the kinetic friction force as similar to the maximum static friction force, where there's a fixed value. And then here are some coefficients of friction just for your information. So we have rubber on concrete, so like car tires. Coefficient of static friction is 1, coefficient of kinetic friction is 0.8. And we have steel on steel when they're both dry. There we have static is 0.8 and kinetic is 0.6. And then steel on steel when there's some sort of lubrication between them, we get way smaller coefficients, 0.1 and 0.05. And then wood on wood, etc. But one thing I wanted to point out with this, well, two things. First is there are no units for coefficients of friction. So it's just based on where they come from, the units cancel out. So they don't change our units at all. And they don't have their own special units. But then the other thing is that the coefficient of static friction is always bigger than the coefficient of kinetic friction. So it's just, what that means is that it's harder to get something going. So you have to overcome a bigger force of friction to get something going than you do to keep something moving. Okay. So now we're going to do some examples. And I will show you the examples on there because there's something I want to do before this one. 1 second. Okay. First, I just want to look at a situation where a person is just standing on an incline and look at how we treat this sort of situation. So we're on an incline, so we're going to tilt our coordinate axes. So what you're really doing is just making your x-axis along the incline. So this is still that angle theta. And then our y-axis is perpendicular to our x-axis. And then let's start with the forces that might be a little bit easier. So normal force perpendicular to the surface. So not straight up, but perpendicular, which is along our positive y-axis. So this is the normal force. And then this person isn't moving, so they're experiencing static friction. And we know that an object would slide down an incline if there wasn't friction. So the static friction force is going to point up the incline. So Fs. And then we have the weight force, and the weight force points straight down. And so that's what I was showing on the slide is the weight force here, and then the angle theta there. So the other thing I wanted to do, well, just showing you a free body diagram first before we're like doing a problem with this. But then also sometimes people get caught up on like why this is the angle, like why when I tilt the axis, is it then the angle from the y-axis that contributes? So I just wanted to show you how that works. So I'm gonna make it bigger. So there's our x and y axes. And then here is kind of our weight force. So it's this here pretty much, not at an angle. So this is that theta of the incline. And this I'll call phi. That's the symbol phi. And I'll call this one alpha. Okay, and then we know these ones are 90, and we also know that these two added together are 90. So that's actually the part that we're going to use. So first of all, when you add up the angles in a triangle, it's 180 degrees. So 180 degrees equals the 90 from the corner plus alpha plus theta. Okay, and then we know that a right triangle, a corner, is 90 degrees. So 90 degrees equals alpha plus phi. Alpha plus phi. Okay, well, now let's do a little rearranging of this equation, if you don't mind. Let's subtract 90 on both sides, and we end up with 90 degrees equals alpha plus theta. And 90 degrees equals alpha plus phi. And what this is telling us is that theta equals phi. So this angle here is also theta. So anyway, I don't expect you to be able to recreate that, but it can be helpful to see where it comes from. So now we'll move on to the example. So this time no, there isn't friction, but we're actually going to do stuff still. So a skier slides down a steep 27-degree slope. When a slope is this steep, with snow, friction is much smaller than the other forces, so we can ignore it. And we want to know what the skier's acceleration is. So let's draw kind of a skier, sort of. There we go. And they're going that way, and then we have this angle theta. Okay. Now we'll draw our free body diagram, also at an angle. That theta. Okay, now let's draw our forces. So we have normal force, that's pointing straight up. I'm sorry, perpendicular. That was, just said that. Normal force is perpendicular to the surface, so not straight up in this example. And then the weight force is straight down. So we'll draw that one straight down. And remember, we just saw that that angle there is theta. So now I'm going to just zoom us in on the weight force because we have to look at the components. Wait. Okay. So, and this is just another like breaking the vector into components. So Here's the y component and the x component. And we can see that the x component is opposite the angle. That means it's sine. So weight of x is the weight times sine theta. And then the y component is adjacent, so it is cosine. Weight cosine theta. Okay, and now I'm going to add them to our free body diagram. And I'm going to, instead of make it like a triangle, I'm going to kind of start them at the origin like I do with the other forces in free body diagrams. So y and x. But that's why I wanted to kind of separate out the triangle so we could still see it. But I like to kind of be consistent with my free body diagrams so that the forces all originate from the origin. Okay, now we do our net force equations. So the net force in y, it's not accelerating through the incline. So just like we're usually not accelerating up or down, at least in our examples so far. And so that's 0. And then in y, we have the normal force. And then we have the y component, of the weight force. And then we'll do the same thing in x. This time, though, we do have acceleration because it says that we're accelerating down the incline. So mass times acceleration equals, and the only force in x is the x component of the weight. So just weight x. Okay, so that seems like we can just use that to solve for acceleration. So mass times acceleration is weight x. I'm going to do a little bit of expanding of the weight x part. So that is weight sine of theta. And then weight, remember, is just mass times gravity. So we end up with ma equals mg sine theta. And our masses cancel out because it's the same mass on both sides. So cool. We didn't even need to know how massive the skier was, which is good because they didn't tell us. So acceleration equals g sine theta. So 9.8 meters per second squared, sine of 27 degrees. And this is 4.4 meters per second squared for the acceleration. So it's not really different from what we were doing. We just have to incorporate another kind of component, I guess. So now another example where we're gonna deal with friction this time. We had to get comfortable with inclines first. Okay, so in this example, I already drew us a picture. A 50-kilogram file cabinet is in the back of a dump truck. The truck's bed is made of steel and is slowly tilted. What is the magnitude of the static friction force on the cabinet when the bed is tilted 20 degrees? And then the cabinet begins to slide when it's at an angle, or when its angle is 40 degrees. So we want to know the acceleration for that. So I already gave us some stuff, so I drew the picture. And then I also got the coefficients of friction for steel on steel when it's dry, because it doesn't say it's like pouring down rain or something. So now this is when it's at 20 degrees. So free body diagram at an angle. Here we go. This is theta equals 20 degrees. Okay, so what forces are acting? Normal force perpendicular to the surface. Normal. Weight force pointing straight down. Weight. And the angle there. And then we have a static friction force pointing up along the incline. Fs. And then I'm going to break up the weight force again. Like I'm going to kind of do the zoom in on the triangle thing. I'll do that probably the first few times that we're working on this, but then eventually I'll just draw it on the free body diagram. But I want you to get more comfortable with it first. So that's the negative y-axis. here's the weight. And so this is, and this is theta. So this is the y component of the weight, and this is the x component of the weight. So y is cosine, and x is sine. Okay, now I will draw them, and I inverted my colors over here, so sorry about that. So, this is the y component, and then the x component. And you can kind of see that in my free body diagram. I think my normal force vector is too big, but I don't want to erase everything. So we're just going to leave it for now. Actually, you know what? It wouldn't be that hard to fix it. Let's fix it. Let's just make it, because again, we know it's not accelerating through the truck. So these forces along the y-axis should be about the same size. I think that's close enough. And we didn't do this in the other example, but the net force, F net, is along the incline, along the truck bed. Okay, now sum of forces. Oh, wait, I'm sorry. It's not moving. Static friction. So the net force for this one is 0. There we go. So now our forces. F net y equals 0. And in y, we have the normal force and then the y component of the weight. And then F net x equals 0 also. And this one, we have the x component of the weight in the positive x, and then minus the static friction force. Okay, and this problem is asking us first for the static friction force. So we have an equation for static friction. We just learned it. But actually, we can just use this equation here because we know what the mass is. We know weight is mg, and we know the angle to give us the x component of the weight. And so we can just use this to find the static friction. So 0 equals the weight in x minus the static friction force. And then we'll add static friction to both sides. And we get static friction is the x component of the weight, which is the weight times sine theta, which is mg sine theta. Now we can plug it in. So the file cabinet is 50 kilograms. Yes. 50 kilograms times 9.8 meters per second squared times sine of 20 degrees. And this gives us a static friction force of 167.6 newtons. So that's what our static friction force is at an incline of 20 degrees. Now we want to find the acceleration when the incline is 20 degrees. Yeah, I think I can make some of it fit on here. So I'm just going to draw again because now we have a different angle, and I don't think I really drew it at 40 degrees. My angles are far from exact. Theta equals 40 degrees. And we have a different friction force, so we're going to draw it again. So normal force still going up. Try not to make it too big this time. Weight force straight down. Wait. And then we have the coefficient of kinetic friction, or sorry, just the kinetic friction force. The coefficient is involved, just not in our free body diagram drawing. This is theta. And then I'm just gonna do the same thing from before and say, here's our y component of the weight and our x component of the weight. And then the net force this time is down along the incline. Sorry for the confusion before when I was trying to make it slide when it wasn't ready. Okay, so now we can do the net force equations again. F net y, this one looks the same as before. So it's just 0, normal force minus the y component over the weight. The angle's different, so the y component of the weight is not the same, but the equations. F net x equals, so this is not 0, it's mass times the acceleration that we're trying to find, the acceleration, that's not the mass. And then the x component of the weight minus the kinetic friction force. Okay, and we just learned that the kinetic friction force is equal to the coefficient of kinetic friction times the normal force. So before we can solve for this acceleration, we should get a proper equation for the coefficient of kinetic friction, which are for the kinetic friction force. I'm sorry, I keep saying coefficient. And to do that, we need to find the normal force, which is fine because it's right here in this equation. So let's see. 0 equals normal force minus the y component of the weight. If we add the y component of the weight to both sides, we get normal force is the y component of the weight. And that's easy. And let's write what that is. The weight times cosine of theta. Okay, cool. So we have that. Now we can take a look at this equation. So we'll bring that down here. We have mass times acceleration equals, and I'm going to just plug in what the x component of the weight is. So that's just weight sine theta. And then this friction, like I said, is the coefficient of kinetic friction times the normal force. So here's the normal force, but we need to multiply that by the coefficient of kinetic friction. Weight cosine theta. And then let's also expand out the weight. So that's mg sine theta minus mu. That's what that symbol is, by the way, mu. Hey, mg cosine theta. Yes, I did that. Cosine theta. Cool. And we have mass on both sides, so we can divide that out. So that's why I wanted to expand out those weight equations so that we could cancel out the mass. So now we have an equation for acceleration. And I'm also just going to factor out acceleration due to gravity because it's in both terms. I'm not canceling it out. I'm just putting it in front sign. So g parentheses sine theta minus the coefficient of kinetic friction cosine theta. That's all. And that way, when you plug it into your calculator, you only have to put 9.8 once. So 9.8 meters per second squared, sine of 40 degrees minus 0.6 coefficient of kinetic friction. And that is no units on that. 9.8. Oh no, see, I was writing it again. Then just times cosine of 40 degrees. So this gives us an acceleration of 1.8 meters per second squared. So the dump truck or whatever it is tilted to 40 degrees, but it's still not sliding that fast. Actually, probably like a reasonable speed for it to be sliding at, maybe. You don't want a 50-kilogram file cabinet to race down the back of the truck. Probably dangerous. Okay, so that is the combination of working on inclines and friction. That is all I have for you. Have a great day.